Hi class, this is Mr. Morris. Today's topic is stoichiometry. It's AP topic 4.5, stoichiometry. I wanted to make a video of notes going over this in the way that we learned it last year. To start with, let's talk about something called moles of reaction. This may be a new word to you. We didn't use it a lot last year. So let's consider this reaction. In the reaction above, you can see that if I have 4 moles of Fe and 3 moles of O2, I can produce 2 moles of Fe2O3. 1 mole of reaction means that I've got 4 moles of Fe combining with 3 moles of O2 to produce 2 moles of Fe2O3. So 1 mole of reaction involves the exact coefficients that are given in the equation in terms of moles. That's what it means. 1 mole of reaction is whatever the coefficients say in terms of moles. So 2 moles of reaction in this case, 2 moles of reaction would be if I had twice as many moles as what the coefficients in the equation say. So if I had 8 moles of Fe available, 6 moles of O2, that would produce 4 moles of Fe2O3. That's 2 moles of reaction. A mole of reaction is kind of analogous. It's almost the same thing as a batch in a cooking recipe. Let's say that you have a recipe that makes 12 cookies, makes a dozen cookies. That would be 1 batch of cookies would make a dozen cookies. 2 batches would make 2 dozen cookies. It's kind of what we mean when we say a mole of reaction. It's 1 batch, and it's in terms of moles. So how do we determine the number of moles of reaction? Well, you're going to take the moles of the substance that we're referring to. In this case, it would be either Fe, O2, or Fe2O3. You take the substance you're dealing with that we have information about and divide the number of moles of that by the coefficient that's given in the equation. That will tell you the number of moles of reaction. So the same reaction that we just talked about, let's calculate the number of moles of reaction. If I have 2.50 moles of Fe, so 2.50 moles of Fe, and my coefficient is 4. So I'm going to say 2.50 moles of Fe divided by 4 moles of Fe, and that gives me 0.625 moles of reaction. That's how you calculate the moles of reaction. The next part asks us to calculate the number of moles of reaction that occur when 2.50 moles of O2 are consumed. So I have 2.50 moles of O2. Find the coefficient for O2, which is 3. It's going to be 2.50 moles of O2 over 3 moles of O2 to give us 0.833 moles of reaction. We could also find the number of moles of reaction if we had 2.50 moles of Fe2O3 being produced. Take 2.50 moles of Fe2O3 divided by the coefficient for Fe2O3 is 2, so 2 moles of Fe2O3 will be in the denominator. You end up with 1.25 moles of reaction. By the way, I didn't say it earlier, but please feel free to pause this video if you need to catch up, and we're going to do some example problems. I want you guys to pause the video, try it out, and then check your answers. We have some guidelines for stoichiometry. I want you to keep these in mind. It sounds like a lot, but once you get in the habit, it shouldn't be quite as much. And I think seeing it the second time will make more sense to you. First, we need to determine the given in the problem. It's either the information provided in the problem for that specific element or substance, or you have to determine the given because you've got to figure out what the limiting reactant is. We'll talk about the difference between those types of problems in a little bit. Once you know what's given, you need to convert to moles. Always. Always, always, always. The way you convert to moles depends on the problem, but you always have to convert to moles before we can use the chemical equation. You can either use molar mass Avogadro's number, PV equals nRT, or the molarity equation. Molarity equals moles over liters, and you would be looking for the number of moles. The next thing we're going to do is set up the balanced equation with the moles of given and the asked substance on top, and the moles of coefficients of the same substance on the bottom. It's basically the same thing as the moles of reaction being set equal to X over the coefficient for whatever it is we're looking for. And you solve for moles of what is asked in the problem. So basically you're solving for X. After you find moles, we will change the asked value into whatever unit the problem's looking for. And we're going to use the same things we did up here. You use molar mass if it's grams. You can use Avogadro's number if you're trying to find the number of particles. We can use PV equals nRT if I'm looking for pressure, volume, or temperature. Or we can find molarity using the molarity equation. Limiting reactant problems. How do we know if it's a limiting reactant problem? And I need to determine that first. Well, you know that you have to find which one's the limiting reactant if you have amounts given for 2 or more reactants. So 2 or more amounts are given for reactants in the problem. How do we find the limiting reactant? Well, we want to find the moles of reactants involved. Basically, you divide the moles of reactants with the coefficients from the balanced equations. It's basically finding the possible moles of reaction for each reactant that is given. And the reactant with the smallest mole over coefficient is the limiting reactant. In other words, the reactant that gives you the smallest number of moles of reaction is the limiting reactant by definition. After we've done that, everything is going to be calculated using the limiting reactant. Moles of limiting reactant over the coefficient set equal to X over something. Let's do an example. This one is not a limiting reactant problem. It's just a straightforward stoichiometry problem with a couple differences from what you maybe saw last year. The next example will be a limiting reactant problem. So it says when 75.6 grams of CO2 is produced from this combustion reaction that's given above, we want to calculate the following. Let's start with A. That's the volume of oxygen gas used at 545 Kelvin and 2.00 atmospheres. Then we're going to find the mass of the water produced and also the number of molecules of butane that are consumed. Starting out first with part A, I know what's given is grams of carbon dioxide. No matter what is given, we are always going to start by converting it to moles. So I've got my grams of carbon dioxide. I'm going to use molar mass to find the moles. So you calculate the molar mass. It's 12.01 grams of carbon plus oxygen. If I've got 2 of them, that's about 32. So 12 plus 32, you get 44.01 grams is the molar mass of carbon dioxide. So we're using that molar mass to convert from grams of carbon dioxide to moles of carbon dioxide. So the essential first step is always find moles of what is given. In this problem, I want to find out how much oxygen I have. I want the volume of oxygen, but before I can find that, I've got to find the moles of oxygen. So find oxygen in the equation. It's going to be X moles of oxygen over 13 moles of oxygen. So our equation is going to be what's given in the problem over the coefficient equals what I'm looking for in the problem, that's X, over the coefficient. So I have 1.72 moles of carbon dioxide, that's what I just found, over the coefficient for CO2, which is 8 moles of CO2, and that's what I'm going to use in every part of this from now on. It's the given moles over the coefficient equals X moles of O2, I'm looking for O2, divided by 13 moles of O2. We're going to cross multiply and then divide by 8. You find that the answer would be 2.80 moles of O2. I'm specifically looking for the volume, and I have temperature and pressure. So I'm going to use the ideal gas law, PV equals nRT. Let's list out our variables. I have pressure of 2.00 atmospheres. My volume is my unknown. I just found the number of moles of O2 by doing stoichiometry, 2.80 moles of O2. I have the ideal gas law constant, which is R equals 0.08206 liter atmospheres per mole Kelvin, and my temperature is 545 Kelvin. Now I can plug that into my equation. It's going to be PV equals nRT, so that's 2.00 times V, my unknown, equals 2.80 times 0.08206 times 545, and that's what we have here. In order to solve, I'm going to divide by 2.00 to find what V is. So I get this. Put that in your calculator and you will find the volume to be 62.6 liters of oxygen. That's part A. Part B asks for the mass of water produced. We're still going to use the number of moles of CO2 that we calculated in the previous step. Moles of CO2 divided by 8 moles of CO2 equals, now I'm looking for water, so that's going to be X moles of water, always start with moles, X moles of water over 10 moles of water. So the moles we used in the last step, 1.72 moles of CO2 over 8 moles of CO2 equals X moles of water over 10 moles of water. Cross multiply, and then we're going to divide by 8 once again. You get 2.15 moles of water. I want the mass of water. So now I'm going to multiply by the molar mass of water, which is 18.016 or 015, okay, depending on which periodic table you're using, and you end up with 38.7 grams of water. Okay, part C in this question, the number of molecules of butane that's consumed. Again, we're going to use the moles of the given, which is carbon dioxide. I believe it was 17, let me check. Yeah, no, 1.72 moles of carbon dioxide. 1.72 moles of carbon dioxide over 8 moles of carbon dioxide. And we're setting it equal to moles of butane. Well, butane is this over here, so it's going to be X moles of butane over 2 moles of butane. Cross multiply, divide by 8. You end up with 0.430 moles of C4H10. In this case, I'm looking for the number of molecules of butane. Okay, so if I want to find the molecules, I'm going to have to use Avogadro's number. Make sure you're canceling out your units with dimensional analysis as you do this. 4.30 moles of butane times Avogadro's number of molecules over 1 mole, and you end up with 2.59 times 10 to the 23rd molecules. One thing I want to emphasize, make sure that you are labeling your units in stoichiometry. There's a lot of different ways to show your work with stoichiometry, especially as we get into more complicated types of stoichiometry problems. There's a lot of different ways to show your work, so it is very important you label your units so that the AP graders can follow your logic. Alright, a sample containing 12 moles of aluminum and 12 moles of hydrochloric acid, HCl, are mixed in a beaker. We want to determine the limiting reactant and justify with calculations. Calculate the moles of H2 gas produced. And we want to find out what the excess reactant is and how many moles are left at the end of the reaction. And finally, draw a diagram of what remains in the beaker after the reaction has occurred. So this is the first one that we're doing. That's a limiting reactant problem in the set of notes. But the good news is it's already in moles. That saves us a step. If it's already in moles, you can dive right into setting up your problem. 12 moles of aluminum over 2 moles of aluminum. Okay. Now I want to find the limiting reactant because I have two different reactants. They're both on the reactant side. I've got two amounts of reactants given. We want to know which one's going to run out. That's our limiting reactant. So I'm going to do 12 moles of aluminum over 2 moles of aluminum, and I'm going to do 12 moles of HCl, 12 moles of HCl over 6 moles of HCl. So when you do 12 over 2, you get 6, and 12 over 6 is 2. Which of those is going to be the limiting reactant? Well, it's the one that makes 2 moles of reaction. Okay, this is really important. I want to make sure that you get this. When you do a limiting reactant problem, this answer that you get when you divide 12 over 2, this is not moles of aluminum. If you put moles of aluminum, it will be counted wrong. When you do 12 moles of HCl over 6 moles of HCl, the answer is not moles of HCl. If you put that, you will get it wrong. These actually could be written as numbers with no units because the units technically cancel out, or you can write moles of reaction. Either of those answers are acceptable, but you cannot put moles of aluminum or moles of hydrochloric acid. That would be incorrect. So the one that's the limiting reactant is this one over here. Another thing, when you are asked to determine the limiting reactant, you have to explicitly say hydrochloric acid is the limiting reactant, or HCl is the limiting reactant. Do not assume that they are going to know the answer just from this much work. And also, if you say 2 moles of reaction is the limiting reactant, that is incorrect. The limiting reactant has to be one of the reactants, so it has to be a substance that is on the reactant side. It's either aluminum or hydrochloric acid in this case. It's hydrochloric acid because it yields the fewest moles of reaction. All right, calculate the moles of H2 produced. From now on, we're going to use the limiting reactant as our given because the whole problem depends on the reactant that provides the fewest moles of reaction, or the limiting reactant. So I'm going to use my 12 moles of HCl over 6 moles of HCl and set it equal to X moles of H2 over 3 moles of H2. And then I'm going to solve. Cross multiply and then divide by 6 to get 6 moles of H2. I want to know, actually that's exactly what I wanted to know, just moles of H2. Next step, what's the excess reactant? The excess reactant is the other reactant, the one that's not limiting, it's left over. So aluminum is the excess reactant. And it asks me how many moles are left. Be careful with the wording here, make sure you pay attention. This is not asking how many moles are used, it's asking how many are left over. The way we're going to find that is by subtracting the amount that's used from the amount that's given. The amount given in the problem is 12 moles of aluminum. I just have to figure out how much is used and then subtract from that number. The way we do that is by setting up a stoichiometry problem or ratio where we have 12 moles of hydrochloric acid, our limiting reactant, over 6 moles of hydrochloric acid. If that's all used up, how much aluminum is used? So we'll do X over 2. 12 moles of HCl over 6 moles of HCl equals X moles of aluminum over 2 moles of aluminum. Cross multiply, divide by 6, and you get 4 moles of aluminum being used or consumed by that hydrochloric acid. To find how much is left, we need to subtract the 4 moles that were used from the 12 moles that were available at the beginning. And what we end up with is 12 moles minus 4 moles gives us 8 moles of aluminum left over. Drawing the diagram of what remains, this is a pictorial representation. It's not going to show the exact number of molecules, obviously. It's just a representation of what remains. There's a few things you need to keep in mind. Hydrochloric acid is consumed, so we should not see any HCl in the solution. It's been used up. Hydrogen is a gas. Pay attention to your states of matter. It's a gas. It's going to evaporate. It will be out of the solution. It will no longer be in the beaker. AlCl3 will dissociate. It's going to break apart into Al and 3 chloride ions, 1:3 ratio. And aluminum is a solid. It's the excess reactant, so it will remain at the bottom. Your diagram may look different than this, but this is one way you could show it. You can make a little legend, or you could just draw aluminum 3+ in a circle if you'd rather do that. We'll draw our beaker with a couple aluminum ions, and we've got 3 times as many chloride ions, and we got a little bit of aluminum metal as a solid at the bottom. Another example here, example 3. In a beaker, we have 200 milliliters of 1.50 molar KCl solution mixed with 100 milliliters of 2.00 molar lead nitrate solution to produce a precipitate. We want to determine the limiting reactant justified with calculations, find the mass of lead 2 chloride precipitate that's produced, and then we want to find out what the excess reactant is and how many moles are left at the end of the reaction. Draw a diagram of what remains in the beaker after it's done, and calculate the concentration of all of the ions remaining in the solution at the end of the reaction. So this is a more involved problem. It's the hardest, longest stoichiometry problem in this video. Before we get started, we need to make sure that we have moles. So I have molarity and milliliters of KCl. I have my molarity and the milliliters of PbNO3 To find the limiting reactant, I'm going to have to first convert to moles. So I'm going to use my molarity equation. Molarity equals moles over liters. These are milliliters. I have to first convert those into liters. If you don't remember how to do that, there are 1,000 milliliters in a liter. So we would just divide by 1,000. You get 0.2000 liters. Okay. Do the same thing with the other one, of course. Okay, now we've got our molarity equals the unknown number of moles over the liters we just found, 0.2000. Cross multiply, the number of moles equals 0.300 moles of KCl. Let's do the same thing with our lead 2 nitrate solution. That's 0.1000 liters when we convert from milliliters to liters. 2.00 molar equals N over 0.100 liters. You find that the answer is 0.200 moles of lead 2 nitrate. There's a typo there. That should be lead 2 nitrate, not lead 3 nitrate. Of course, to find the limiting reactant, we have to find the moles of reaction for KCl, and that is the moles we just found, which was 0.300 moles of KCl divided by 2 moles of KCl. That's just our coefficient. We get 0.150 moles of reaction. We're going to do the same thing with lead nitrate. 0.200 moles over, and it's just 1 mole in this case. 0.200 moles of reaction. So the one that gives us the smallest number of moles of reaction is our limiting reactant. That would be KCl. Part B, calculate the mass of lead 2 chloride precipitate produced. So we're going to be using KCl since it was our limiting reactant. It's going to be 0.300 over 2. Don't forget to label your units, of course, equals X for the moles of lead 2 chloride over 1 because there's no coefficient for PbCl2. That gives us 0.150 moles of PbCl2. We want to know the mass, so we're going to have to multiply by the molar mass. And you get 41.7 grams of PbCl2. What's the excess reactant and how many moles are left at the end of the reaction? Well, PbNO3, the other reactant, is the excess reactant. So we're going to use 0.300 moles of KCl over 2 moles of KCl equals X moles of lead nitrate over 1 mole of lead nitrate. That is going to tell us the number of moles used, which was 0.150 moles of lead nitrate once again. The next step is going to be subtracting that from the moles of lead nitrate that was given in the problem. Remember to use the number of moles that you calculated in part A. So we have 0.200 moles of lead nitrate that were given minus 0.150 moles of lead nitrate, which we just found that was used. That gives us 0.050 moles of PbNO3 that have been used up or consumed. I'm sorry, no, that are left, that are remaining. Part D. We want to draw a diagram of what remains in the beaker after the reaction. So we know that lead nitrate is one of the reactants it's the one that was left over. KCl was consumed, so we shouldn't see any of it. We produced lead chloride and potassium nitrate. So let's think about what we're going to see. KCl is consumed, as we said. PbNO3 is going to split apart because it's aqueous. It's a salt that is aqueous. It's dissolved. So we're going to have Pb plus 2 and 2 NO3 minus ions. And KNO3 is going to dissociate in solution in a 1-to-1 ratio. And PbCl2, that's the one that's a solid, it's going to settle to the bottom. We want to make sure that all of the ion charges add up to be 0. So let's look at a possible way to draw this. So you could have done this in any form that stays true to the ratios that we talked about over here in our description. So for every Pb2, we have 2 NO3s. And for each K plus, we have 1 NO3. And the charges balance each other out. And then, of course, we have PbCl2 on the bottom because it is our precipitate. It's a solid. Finally, calculate the concentration of all ions remaining in the solution at the end of the reaction. We have 0.300 moles of KCl over 2 moles of KCl. That's our limiting reactant. Equals X moles of KNO3 over 2 moles of KNO3. This is the one thing that we didn't actually find in a previous step, so we need to find that. It's 0.300 moles of KNO3. We're looking for concentration. We're looking for molarity. So we have to have moles of everything that remains in the solution. I have 0.300 moles of KNO3. Keep in mind, this is aqueous. It's a dissolved ionic compound. And we know that dissolved ionic compounds dissociate. So it's going to split apart into K plus and NO3 minus. We're going to have 0.300 moles of each, of K plus and 0.300 moles of nitrate ions. We also found in a previous step that we had 0.050 moles of PbNO3 that were left over in the solution. We found that in part C. Well, that's going to split apart because this is also an aqueous solution. That's going to split apart into 0.050 moles of Pb and 0.100 moles of nitrate, because there are 2 moles of nitrate for every 1 mole of lead nitrate. So I know how many moles of potassium I have, I know how many moles of lead I have, but please notice that you have nitrate coming from 2 different places. We have to add those together to find out how many moles of nitrate we actually have in the solution. 0.300 moles of nitrate plus 0.100 moles of nitrate gives us 0.400 moles of nitrate ions. Now we can find our molarities. First, we have to know what our volume is going to be. It's 200 milliliters plus 100 milliliters gives us a total of 300 milliliters. That's going to be 0.3 liters. Now, we're going to do moles of potassium over 0.300. That gives us a 1.0 molar potassium ion concentration. The molarity of lead ions is going to be 0.050 divided by 0.3000. That gives us 0.17 molar lead ion concentration. And then finally, nitrate ions, we just found that down here, 0.400 moles of nitrate divided by 0.300 liters of solution gives us 1.33 molar nitrate. All right, that's a look at stoichiometry with a few example problems, some more difficult than others. Try your hand at the practice problems that you're given, and let me know if you have any questions.